Hey guys, today we're going to be creating a neural network from scratch in C Sharp. First caveat of this tutorial, you should know C Sharp. You should be familiar with functions in C Sharp, functions as variables. Secondly, you should have some familiarity with neural networks. I'm not going to explain any of the theory behind them, but you should be somewhat familiar with what they are and what they do. There are two special bits of knowledge I'm going to cover that we need to understand before we can start programming. First is sigmoids. What the heck is a sigmoid? Well, a sigmoid is an equation, a very specific equation, that essentially, given an input, provides a nonlinear output. So in other words, if we were to go to the graph and graph this out, it is not a straight line, right? It's a curved line. In this case, the sigmoid is in the shape of an S, and the default sigmoid equation, as you provide a higher value on the x-axis, it will spit out a value that is closer to 1 on the y-axis. So basically, if we put 9 million into this thing, it's going to give us a value that is extremely close to 1. If we put 0 into this, it's going to spit out 0.5. This is important because there are nonlinear relationships, nonlinear correlations that we need to map out. And basically, if we stick to just a linear equation, we're going to end up with something like the left. We're going to end up with a model that is a linear straight line that is not going to fit our data, which often data is going to be a curved squiggly line, right? So when we put it into a nonlinear equation, we can provide a curved correlation, which is useful for many problems. Second special bit of information is bias nodes. Essentially, sometimes we will have a problem like the XNOR gate where our inputs do not correlate well to our outputs, or in other words, so we have the first row here, we have the A slot and the B slot, and when we put 0 in the A slot and 0 in the B slot, we want to output a 1. But unfortunately, there is nothing you can multiply by 0 to produce a 1. So if you're thinking of a neural network like a complex mathematical function, which it is, you need to realize that we sometimes need to have constants in our little equation so that even if the inputs don't really relate to the outputs that much, we can generate outputs, generate signal that otherwise wasn't given to us. Next thing I'm going to do real quick is I'm going to show you the math in our neural network so that you know that there's no complex math in this tutorial whatsoever. What I'm going to show you is all the math that is involved. It does not get more complicated than this. There is no differential calculus or anything complicated in this tutorial, which is on purpose. When we train our neural network, we will not be using calculus. We will be using a guess and check method. That is so that this tutorial is easy to follow. If you want to dive into that stuff on your own time, that's up to you. Okay, here it is. This is all the calculation that we're doing. We're multiplying weight by a node result value. We're plugging that into our sigmoid equation. We're adding that to the result, and then we're taking the average of that, and that is our result. That is literally all the math here. This is all the code to handle the math. All right, in summary, we need the sigmoid function because we need nonlinear relationships. We need squiggly lines to map well with the data. And we need the bias nodes because sometimes our input does not relate directly to our output, and because you can't multiply 0 by anything to output a 1, for example. Okay, let's build a neural network in C#. First, I'm going to cover the classes that we're going to create today. We are only going to create 4 different classes, and that's it. That's all you will have to write today. And once you write these 4 classes, you will have a functioning neural network that can solve XOR. First class is our net class. This will hold a list of layers. Next is our layer class. This will hold a list of nodes. Next is our node class. This is the most complicated class that we have. It will hold a list of other nodes that it connects to. It will hold a list of weights that correlate to those nodes, and then it will perform the mathematical operation that I already showed you. Finally, we have our simulant class. The simulant class is going to be used in training. It will have 2 lists. One list will be the input that we want to put into our neural network. The second list is going to be the wanted output. So we have inputs in a truth table, like with our XNOR here. So we would have 0 and 0 would be our list of inputs, and then our list of wanted outputs would just be 1. That's it, guys. We can go ahead and get started with coding. All right, here we go. The actual coding part. Obviously, one of the prerequisites here is you need something to create C# programs with. I have Visual Studio, pretty standard stuff. So I'm going to go in here and click Create a New Project. Then I'm going to search for console and then .NET. And I'm going to pick a C# console app using the .NET framework. And I'm going to click Next. I'm going to call this Simple Neural Network Tutorial. And then I'm going to go ahead and click Create. Okay, so here we are in our application. We have a program class here. We have our main method. And the first thing I'm going to go and do is go ahead and create all of the classes that we are going to use. So I'm going to go to Add, New Item, and then I'm going to call the first one. Actually, hold on. I'm going to go to Add, New Class, down at the bottom. And then I'm going to create our Simulant class first. I'm going to change this to be public. And then I'm going to add our node class. Call this node. And I'm going to make that public. And then I'm going to add our layer class. And I'm going to make that public. And let's see, what do we need? And then I'm going to add our net class. Net. And guess what, guys? I'm going to make that public. Okay. First, I'm going to start with our Simulant class. This is going to be the simplest class that we have. So I'm going to set up a public list of inputs, and I'm just going to call it inputs. And the get and set is just because this is a property. And then I'm going to create a list of doubles that is the wanted outputs. And there we go. Boom, 25% done. We finished one of 4 classes. All right, let's go to our node class next. And our node class is going to be one of the more complicated ones. First, we're going to set up a dictionary that references other node classes and maps our weights to it. And I'm going to call this input nodes. And we'll go ahead and initialize it so we don't get any weird initialization bugs going on. So here we go. Equals new dictionary, and it's still a property here, as you can see. Next, I'm going to declare a double variable called result, and this is just going to hold the result of the node after we calculate on it. And then the most complicated variable that I'm going to add here is a function variable. So this takes a C# function method, same thing. And that method is going to take a single argument, which is a double, and it's going to output a single argument, which is a double. And we're going to call this our sigmoid. And we're going to leave it blank, no initialization. It should default to null. All right, and then we're going to go ahead and build our constructor for our node. And the constructor is going to take a function, which will be our sigmoid, and then it's going to take a result, which we will use later, but we're going to initialize that to 0. And we'll set the sigmoid to the sigmoid, and we'll set the result to the result. And boom, that's it for the data. Let's see here. We'll also want a couple different functions here, two different methods. One is going to return void, and it's going to be called add input node. This is going to make it a little bit easier on ourselves later, and we're going to add an input node. We're going to add the node that gets passed in, and then we're going to set its default weight value to be just a very low number. I'm just going to do 0.0001, and that's it. That's all this will do. All right, and then now for the math part of the deal here, we're going to go ahead and make public void, and we're going to call this calc node. And this is the math segment that we already went over a little bit here. But basically, first step, we're going to traverse all the nodes that are connected to this node. So for each node in our input nodes, and I'm going to go ahead and select, I'm going to change this from node actually. I'm going to call this value pair because this is a dictionary, so it's actually going to be two different variables. And then to split that out, I'm going to declare a node variable, which I'll grab from the value. So again, there's the node and the double, and the value is going to be, oh, that's the double, so I need to switch that. Sorry, so we're getting the node, and that is the key, and then we're getting the weight, which is the value on the value pair. Next, we are going to add to our results the result of our sigmoid function, which when this node gets created should be declared. And we're going to do weight times node.result. So this node our input node, will have already calculated itself. This calc node will have already been called on it, or it will be an input node and we will have manually set the result ourselves, which we will cover later, of course. And so we're just going to take the result for the input, multiply it by the weight, put it into the sigmoid, and add it to our result tally. And then we are going to take result and set it to be an average. So we want to divide by input nodes.count to give us our average. But just in case there aren't any input nodes, which might be possible for our first level, our first layer, I'm going to use math.max, and whichever of these is bigger. So if the count is 0, it'll put 1. And if the count is bigger than that, then it'll use the count of however many input nodes we have. And then I'm going to do one more thing for safety. So when you're playing around with this, you might set sigmoid to be some sort of unique function, or you might set the depth of your neural network to be really, really deep. And sometimes what will happen is you end up with values that are basically invalid. So if somehow your weight is ever dividing by 0, we want to detect that, and in that case, double is going to be set to nan, which stands for not a number. So we want to check if it's nan. We want to check if it is infinity, because that can happen. And we want to check if it is negative infinity, which can also happen. So we check all that in an if statement. And if any of these are true, we want to go ahead and throw a new exception. And I'm just going to write in some text and say, hey, bad result. And that way we kind of warn ourselves if something goes wrong. All right, that is the node class. That is literally it for the node class. We are done. 2 classes down, 2 more to go. These might get a little complicated, but we're gonna dive right in, right? So our layer class. Let's take a look at the variables here. For our layer variables, literally all there is a list of nodes. So that's easy. We're gonna get set. We're gonna go ahead and initialize this to a new list of nodes so that there's no initialization problems later on. And then we're going to create the constructor for this. So when we make a layer in our network, we want to be able to tell it how long we want it to be, the width of the layer. So I'm going to go ahead and create a width variable that can get passed in. And then for this width, we want to go ahead and create that many nodes within our layer. So I'm going to go for int I equals 0 while I is less than width, I plus. And then for each of these, I want to create a new node. So I can make a new variable called new node and call the constructor of our node argument. And then once we have that, we're going to add that to our list of nodes. Easy peasy. So let's see, what does the node want to be constructed? It wants a sigmoid and it wants a result. We are not going to use the result yet. We're going to leave it at the default, which is 0, but we do want to pass in a sigmoid function. So to do that, let me actually change this. We will use our lambda expression and then create a new function here. This function is going to input a single argument, which is a double. I'm going to go ahead and call it x. And then I'm going to write out here mathematical sigmoid function. Okay, and it doesn't like us. Oh, we haven't returned anything yet. So we're going to return a sigmoid function. I am going to modify the sigmoid function a little bit. I'm going to make it so that it ranges from 5 to -5. So let me go ahead and open up the Desmos calculator because I should probably show this to you guys. I'm going to Google Desmos sigmoid, and that's going to take us to the default sigmoid equation here, as you can see. And I'm going to make a modification. So at the top it says 1 right now, but I'm going to make that 10. And as you can see, that's going to bring our graph up here. And then I'm going to subtract 5, and that is going to center it on 0. So if we input 0, 0 will be output. And then that'll give us a little bit broader range for our sigmoid. And that's just something I like to do. Keeping it from between 0 and 1, I'm not a huge fan of. So this still gives it reasonable limits and keeps it from, producing values that are too large. But it gives us a nice, good range between, the negative and positive numbers. So I'm going to go ahead and input that into C#. And bear with me here. We're going to convert the equation we just saw into programming language, which is going to be a little bit of a task here. We got to make sure we get all of our parentheses correct, which is going to be a nightmare. That's 5. Boom. And swap input for x. Okay, so that's what it looks like. Return, and then you can do your parentheses. I guess I don't need this parenthesis here. I always like to add extra parentheses, more than I need usually. Maybe I'll zoom in on that a little bit. take your time typing that out. Okay, sweet. So all the nodes that we create in our layer, which is a specified width, are going to use this sigmoid function that we just passed it. Now, if you want, you could put some sort of if statement here or some sort of randomization and pass it your own unique sigmoid. You don't have to do, 10 and -5. I just know this will work. But if you want to do something else, I mean, be my guest. But I know this will work for our example, so we're going to do that. Okay, next thing we need to do. So we had a function for calculating each individual node, and we actually want to do that for calculating each individual layer as well. So I'm going to create a function that returns void. I'm going to call it calc layer, and for each node, for each of our nodes, we're going to go in here and all we got to do, because the node does the hard stuff, is we just got to go in here and call node.calcNode. That's it. Easy peasy. And this will just make it so that when we're in our net class, we can just call each layers thing, and that way we don't have a for loop within a for loop within a for loop or anything crazy like that. This is architectural decisions, right? The complicated thing that we need here, though, in this class is we need a way to link the layers together. So if you remember in our node diagram, all the nodes connect to nodes that are in the next layer, and they've got all these little lines connecting them. And so when we're constructing our net, we want a way to tell one layer to link to another layer. And the way that I've set this up is rather than looking at the layer that is ahead, we actually look at the layer behind us. And so because of that, this might be, I don't know, a little confusing, but let's start out with our for each loop here. We're going to take, or we're going to go ahead and iterate through every node, and let me call this last node, in last layer. So the last layer is looking backwards in our neural network, looking at a layer that is closer to the inputs. And we're going to iterate through every node in the previous layer. And then for every node in the previous layer, we're going to also iterate through each of our nodes in this current layer. And for each of those, we are going to add them to last node as an input node. So I think that this will make a little more sense once we call it, but it could be that I have the names mixed up here. Maybe it shouldn't be called last layer. Maybe it should be called next layer. Oh, yep. This should not be last layer. This should be next layer. Oopsie daisy. Let's rename those. Next node. Okay, let me say what this does again. Okay, so we're linking the layers. We will receive, we will look at the next layer. So this function will receive the next layer. For each node in the next layer's nodes, we are going to go through our nodes and add our nodes to the next layer's list of nodes. And so those nodes are looking for input nodes. So we're setting our nodes as the input nodes for the next layer's nodes. Super clear, clear as mud. But I guess all I have to say about this is go back and look at the neural network diagram again, and it'll make a little more sense what we're doing. But I apologize, this is a little complicated, but it is what it is. Okay, guess what, guys? We finished with the layer class. We are all done with that. So let's see, what does that leave? The net class? Is that our last class? I think it is. Probably, definitely the longest class, because this class is going to have the training algorithm in it. It's going to have the scoring algorithm in it, and it's also going to have the method to get the results, the output of the neural network. So yeah, this is going to be the hardest one, but once we're done with this, we're we're pretty much finished. So keep that in mind. Stick with me. Okay. First, input size. We want to know how big the first layer of our network is going to be. Next, we want output size. We want to know how big the last layer of our network is. And finally, we want the depth of our network. All right. So the first and the last layer, we can go ahead and hard code. I'm just going to say layer 1. And it's going to want to know what do we set the width to. So we're going to set it to input size plus 2. So if you remember when I was doing the intro, I talked about bias nodes and how we were going to tack on the bias nodes to the inputs. So we're adding a plus 2 so that we can add 2 different bias nodes to the inputs. So the input of the net is actually going to be bigger than what we ask it to be because of the bias nodes. Forgot an equal sign here. And then, of course, we've got our list of, oh, we need a list of layers. I apologize. Should have done that first. Let me see. Public list layer layers equals, and then we're going to initialize it. Okay, so we've got our list of layers, and then we're going to add our first layer, layer 1. Done. Next, we're going to do the middle layers here. Maybe I'll call this input layer. Okay, we've got our middle layers, and then that we can just do a loop, and we're going to use depth as our meter for that. And we're going to create a middle layer variable, which is a new layer. And how wide do we want the layers to be? Well, for this particular application, we know that we're just solving an XOR. I'm just going to hard code this. I'm going to say 3. And then we're going to add our middle layer here. And then finally, we have the output layer. Output layer equals new layer. And this one is going to be the output size variable that we ask for. And then we can go ahead and add our output layer. Okay. Let me fix that. Okay, that's all done. But there's one thing we need to do additionally, and that is we need to go through all of our layers and link them together. So we've generated these layer objects, but they're not actually connected to each other. And so if you remember in our layer class, we created this link layer method. So this is where we're going to call this. And this is going to tie everything together. This is going to create all those nice lines in the diagram. And this is going to actually network our net together. Okay, so we're just going to go ahead and do another for loop here. But this one, instead of starting at 0, we're going to start at 1. And that's because we're actually going to be looking at 2 items in the list of layers at once because we're linking them together. So we need to reference 2 at once. So we're going to keep going until we get to layers.count, and then we will have iterated through the entire list of layers, one at a time, but we'll be looking at 2 of them. So first we're going to do last layer, and that's going to equal layers and the index minus 1. So because we started at 1, for the first iteration of the loop, that's going to be equal to 0. And then next layer is just going to be layers, and then we'll use I as our normal index. then all we got to do here is last layer, and then we call link layer and pass in next layer. And that'll link all of our layers together, which will be super nice. Maybe I'll add a comment saying what this does. Link layers. There we go. Sweet. Okay, our constructor is done. Yay. We need to create something that will actually calculate the net and get all of our results. I think that's probably the best step to take next. So the results of the network, for the sake of the tutorial, it's just going to be one, but we want to make a network that can handle any output size. So it's going to output a list of doubles, and that's going to be all the outputs from our network. And I'm going to create a function here called getResults. We're also going to take all the inputs, and so we're going to need to load all these inputs into our network, calculate all the layers, which will calculate all the nodes, and then grab our results from the network. So this might actually get a little bit complicated. First thing we want to do is load the inputs into our network. So first I'm going to grab the first layer of our network and throw it into a variable, layer 0. We're going to go ahead and make an assumption here, and that assumption is that there is a layer already in our net. And then we're also going to make a new list for our local inputs. We're basically just going to copy them. Okay, and then the reason we're needing to make a copy is because we're going to add to that list, and we don't want to mess something up somewhere else in the program. So we're going to add our bias nodes, and so those are going to have the value -1 and the value 1. See, if I didn't tell you this in the beginning, you guys would be like, why are you doing this? But now it makes perfect sense, right? Hopefully, maybe. We're going to go ahead and go through all our local inputs now in a for loop. And we're going to look at the first layer. We're going to look at all of the nodes, which should add up. So the inputs here should be the exact same size as the first layer nodes. So we're going to go and set the result of those nodes to be the local inputs at, whatever position. So we're loading each of these inputs into the first layer's nodes at this particular index, at this particular position. Hopefully that makes sense. Next thing we're going to do is we're going to actually do the calculation for our net. So we're going to work our way through all the layers. So we'll do another for loop here and go through each of the layers, reusing the I variable. So var layer equals layers I. That's we maybe don't have to do that. We don't have to select it like that. We could just do layers I and then call calc layer on it. Okay. So we're calculating layer by layer, starting at the first layer at the 0 index and working our way to the end of the neural network's list of layers. Okay. Now now that we've done that, I'm going to go ahead and grab the last layer. So I'm going to do dot last on this list, which is nice. And then to get the results, we need to look at the last layer. We need to go through all of its nodes, and we need to select the result variable from all of these nodes. So each of these nodes, we can call them node. So we're selecting. We're going to node.result, and then we're putting that into a list. So in case you're not familiar with select, this is basically we're doing a for each loop, and each item in that loop is just going to be called a variable called node. So then we take that item and we're returning, we're kind of mapping and returning from that the result from this node. And so that's selecting us a list of doubles. And then we call toList because we want it in a list form. Otherwise, I think it's like IEnumerable or something. Yeah, but I just like to use list for everything, so I just always throw it into a list instead. And I can't say I've ever needed anything other than a list, like lists and dictionaries and everything else. I'm like, why would you even use these? But I'm sure there's other use cases that could be considered. Okay, and the final thing here we need to do for getting our results is we need to clear the results. So each node has that result variable in it, and while we're calculating the network, we want to keep the result that we calculated so that the next layer can use it. But now that we're done with it, we need to go back and kind of clean up all our mess and clear all the results. And if we don't do this, your net is it's not gonna work right. It'll work right the first time, but then every other time it is not gonna work. So we're going to be good, responsible citizens, and we're actually going to go do a double loop. So for every layer, we're going to look at all that layer's nodes, and then for each node, we're going to go and set the result to 0. I'm going to do that manually. And then we're going to return the results of calculating the network. And that's it. We're done with the get result function. One more, and then we're basically finished. I mean, we got to do some logic where we plug in the XOR and we, print some things to the console, but yeah, we're getting really close. Unfortunately, the next one, oh, sorry, two more. My mistake. Two more we got to do. The next one is going to be our training algorithm. I'm going to suggest that you maybe come back and revisit this if you have an interest in this, and maybe redo this and make it better. But for now, you might just want to go in here and kind of copy along and see what I'm doing here. So first, we're going to have a list of simulants. Simulants are our training data, so we're going to call that training data. Next, we're going to have what I call an acceptable score. So that's going to be a double that we take in. And the way this works, how we get the score, is we calculate the distance between the wanted outputs in each simulant versus the output that we actually got, and we calculate we get the distance between those two values, and then we add all the distances together, and that will be our score. The trick is, the lower the score, the better performing the net actually is. So we actually want the lower score, and we're trying to lower the score as much as possible. And that's because we're lowering the distance between the outputs we wanted and the outputs we actually got. All right, this is going to be, we're not going to do differential calculus or algebra or anything here. Okay, we're just going to go and take more of a brute force method, and that is going to work perfectly fine for the case of XOR. We don't need anything that is not brute force. Like, it'll work perfectly fine. That said, we're gonna have to go like 1, 2, 3, like 4 loops deep. Okay, so the first loop is while true. So basically, keep doing this. It's a brute force approach. Keep doing this until we tell you to break. Then we got to decide, well, when do we break? I guess we can figure that out a little later. First, let's get all except the very first layer. So the reason we're getting everything except for the very first layer is because the very first layer is our input layer and we have no interest in modifying it. So we're going to go ahead and use a fancy bit of indexing here. Oh, I need to be on C# 8.0 or greater to use this. Okay, no problem. Okay, I'm back. After a brief bit of research, it looks like I cannot upgrade the C# version to handle this. So we're going to do a little bit of a workaround, and we're going to use the .skip method, and we're going to pass 1. If you had chose to create a C# console app that was not .NET Framework, you probably would have been able to use the, bracket dot dot 0 dot dot 1 dot dot whatever. I don't even know what to call that syntax. But because I did not pick that, we are going to have to do this. This is going to return everything except the first element in our list. So if we look here at the description, bypasses a specified number of elements in the sequence and then returns the remaining elements. So we're going to get all except for the first layer. We're going to skip the first layer because it's the input layer. Next, we're going to do a loop. We're going to look at all the layers in our layers variable. Then we're going to look at all the nodes in that var node in layer.nodes. Look at all those nodes. And then every single node also has a bunch of different connections. So we're going to look at all the connections that that node has, and we're going to look at all the keys and input nodes, and that'll give us all the nodes that that node is connected to. And then using that key, we can actually get the weight values from this dictionary here if we want to. So we're going to be using a guess and check method. So the first thing we need to do is we need to get a score. So we need a get score method. So that is going to take our training data and give us back a double result. Let me put double here. So I'm going to go to this little light bulb, have it generate the method for me, and then jump to that. So it's not implemented yet, but we will go back and fill that in later. For now, let's keep trucking. All right, so the first thing we need to do is get our original score, and then we need to get we're gonna go in, we're gonna change the weight, the multiplying weight of a particular node, right? So to do that, we need to first save the original weight value because we're doing a guess and check method. So first we need to get what the original score is, and we need to keep the original weight so that we can undo the change if the change is actually making the network worse. So first thing we do is we go here and we look at we grab the input nodes original value using our key that we're iterating over here, and we'll get our original weight value, which is a double. Next, we are going to set this particular node weight to be a random value. So I'm going to do input nodes, reference it via the key, and I'm going to add to it, and I'm going to add a random value. Like I said, I'm going to do r.nextDouble. This will give us a random value between 0 and 1, and I want there to be a 50% chance that the value we add to this is negative, and a 50% chance that the value we add is positive. So I'm going to use a ternary operator here, which, might look a little funky, but it is what it is. And I'm going to do another next double, but this time I'm going to multiply it by -1. And then I'm going to do another one, and this one I am not going to multiply by -1. So maybe I should put this on one line, actually. Dun, dun, dun. Okay, so this is checking. If this is true, if the randomly generated number is less than 0.5, so there's a 50% chance. If it is true, we are going to return a number between 0 and 1 multiplied by -1. If it is not true, we are going to return a number between 0 and 1. And we are going to add that to the existing weight value. And then we are going to get our new score now that we have modified that weight. So modifying that weight affects a lot in the neural network because every node is connected to a ton of different nodes, right? So one way to handle figuring out what weight to set is you can do complicated calculus, or you can do guess and check. The problem with guess and check is it takes a long time. It's really slow because we have to check every single simulant in our training data, right? So it can be quite a costly operation. But because we're training it on XOR, I promise you this is going to be really fast. So let me see. Let's get our new score, pass it the training data. Now we need to check if the score is better. Now remember, lower score is better. Less is better. So if our new score was an improvement over our original score, we're going to write something to console. We're going to be like, we're going to say improved node. And that way we know that our training algorithm is working and we can see when we make progress. If it's not better, if our score got worse, we're going to say, uh-oh, we need to go in and undo what we did. So we set up the original, original value, not score. Do not set it to the original score. It will not work. Set it to the original value that we looked up, and that will undo the change that we made. So to reiterate what this is doing, we're making a random change. We're setting a weight to either to a random value between -1 and 1. We're checking if that change improved the score. Remember, less is better. If it did, we're printing out to the console, hey, it improved the score, and then that's it. Otherwise, we're going and if it made it worse, we're going and setting it back to the original value. So this training algorithm will only ever improve the net. It will only make the net get better. So as we run it over time, eventually it will have perfected this network and have the perfect values, or within our acceptable score. Which reminds me, we need a condition to break out of this while loop, otherwise this is going to run forever, right? So every time we go through all the layers and all the nodes and all the output or all the input nodes, we need to stop, take a breather, get the score. So again, we're calling get score. We're passing it the training data again. And then we need to, well, quality of life, let's print the score because it would be nice to know what the progress of our network is as it trains, right? So I'm going to print the score. And then if the score is less than our acceptable percent, again, remember it's less than because a lower score is better. If it's less than what we find acceptable, we're gonna say, hey, training passed. Maybe we could say, we did it. Little smiley face. There we go. And then we'll go ahead and break out of this while loop. I'm just going to call return here. We could also call break if we wanted. Doesn't matter, but I'm going to call return. That is our training algorithm. I guarantee you this will work. I know this will work. Okay, one last method, and then we are done. And then we just gotta, you know, put it all together and demonstrate that it works, right? So the last thing is get score. This won't be too bad of one. First, let's start out with our score. Our score will start at 0 by default. Then we're going to go through every simulant in training data. And then for every simulant, we're going to need to calculate the result of our net. So we're going to need to get the results, and we're going to need to call this dot get results with an S, and simulant dot inputs. So every simulant has the inputs, right? We'll call get results. Let's see what's wrong here. Did we not set up that yet? Thought we did. Get results. Oh, get results with an S. Okay, I'm going to rename it from get result to get results. There we go. And I want it to be plural because it's giving us a list, so I want it to be get results. Okay. We're going to grab our results, and then we are going to go through each of the results that we got back. We're going to compare them to this simulant's wanted results. So we're going to have to do a little bit of math here. I'm going to use some variable names to help us out so that we can call these things normal human names. I'm going to do wanted output, and then I'm going to do the actual output. So we got a list of results, which is a list of doubles. Our actual output is going to be that, and then what we wanted is going to be the simulant wanted outputs at the same index. And then our score is going to be the distance formula, but luckily this is on a single plane, so we can do wanted output minus actual output, and then call math.abs. That stands for absolute value. So this will always give us a positive number, and then we subtract the value, and even if it's a negative number, it'll flip it to positive, and that will give us a distance between the wanted output and the actual output. And we add that to our score, and then we return our score. Whew, that was a lot, right guys? Okay, that's it though. We are ready to go back to our main program here. So I'm going to go program.cs. And a lot of what we have to do now is just some basic setup, housekeeping, call the right functions and stuff, and then we will be done. First thing I'm going to write, hey, program started, so we know for sure. Oh, got a little bit of a typo there. Next, let's see, I'm going to set up a little region here, and I'm going to call it XOR gate logic. If you're not familiar with regions, region just makes it so you can collapse and it'll collapse into a section. It's really nice, actually. If you have, you could make the argument that you should do different functions or whatever, but in this case, I'm just going to do regions. That's my preference. Okay, so we need a list of simulants, which is going to be our training data. So we're going to make that. Next, I'm going to put here in comments all the inputs and outputs for an XOR gate. So that's going to be a little tedious, but here we go. The reason I am not using the magic power of editing here is one, because I am lazy and I hate editing, and two, because I want to walk through absolutely every step with you guys, every mistake. I'm going to be here for it, so that I experience what you guys are going to experience as you create this with me. So we're going to create an object inline. We're going to create our lists here. So the first one is 0, 0, output 0. So first we have our inputs and then our wanted outputs. Now I'm going to copy and paste this. And then we have to go in and very carefully make sure that these match. This should output 1. This should output 1. This should input 0, 1. This should input 1, 0. This should input 1, 1. Please make sure your training data is correct. This is the XOR gate logic. Let me verify. Looks good. Okay, I'm going to collapse this section. Section 1 done. Next section, we are going to, I'm going to create a new region. I'm going to call it generate net and region. Okay, I'm going to call our net network, and I'm going to make a new net. Let's see, input size 2, output size 1, depth, I'm going to set it to 2. Network. Now we're going to train our network with the training data we created. And for acceptable score, do not put 0. It might eventually be able to crack it if you put 0, but it's going to take a long time. We are going to get an approximate value. I'm going to put 0.05. So it'll be very close to 0 without being 0. If you want to put it closer, you can. I just suggest you don't put exactly 0 here. Otherwise, it could take a very long time to get that result. Next, we're going to do test and display results. I'm going to put that in another region. Okay, so we've trained our net. I'm going to say commencing testing. Next, for each data and training data, for our outputs, so we're going to get the results. So we're going to call network.getResults, and we're going to feed it the input data from our simulants. And then we are going to write our output. Wow, actually, first, let me say what our inputs are. So we're going to do data.inputs, and this is just display stuff. So if you're getting a little lost, it's fine. We're just finding a way to display the data so that when it's in console, it looks nice. But it might look like a bit of a mess here. Inputs, and then we want to get our outputs, and we know that it's only outputting a single value, so I'm just using, I'm just referencing array positions that I know exist in the array. and then I'm going to write what we expected in case something goes wrong, or just as a comparison, I guess. We'll put what we expected the output to be, which is going to be data.wanted outputs 0, 0 index. Okay, guys, this is it. This is it. We're going to write finished. Or maybe we could do end of program. I don't know. End of program. And then I'm going to do a console.readline. This just means it won't close until we hit enter. Sometimes it'll close on its own, and I don't like that. Okay, guys, this is it. We're done. Moment of truth. I'm going to hit start. It's going to train on the XOR data, and if everything goes right... Uh-oh, we got a problem, guys. What's the problem? Negative infinity. This field is constant. Oh, oops. I meant to put is negative infinity. Okay, saving that. I'm going to hit back. I'm going to hit start. Oh, and we have another problem. Collection was modified. Enumeration may not execute. Hey guys, okay, I've done some debugging here and I've figured out exactly what is wrong. Originally when I made this, it was in a slightly different version of C#, and I think that might have thrown off a couple of minor things. So the first thing here is originally it was throwing an issue with enumeration. Basically, it thought the dictionary was getting modified, and that makes it upset in a for each loop. So to avoid that, we're just going to add a new list here, and we're just going to copy the keys here, and that should resolve that. And then the other issue that I found was it wasn't actually training, and the reason for that is I wasn't giving it a large enough range here when we're setting the random value. So I'm going to change this from a -1 to a -10. And then I'm going to change this from just next double to next double times 10. And if we run, it'll go ahead and train. And it'll work. Yay! Hopefully yours works as well. If it doesn't, you gotta work at it and debug. Also, additionally, I'm going to be placing the code for this in a repository in the comments. All right, guys, it's been a fun journey. I hope you appreciated this tutorial. Please like and subscribe, and thanks for watching.